Welcome to The Explainer. Today, we're going to completely change how you look at the built world around you. You know, when we walk past a skyscraper or just run into the local grocery store, we tend to think of buildings as these totally static objects, just piles of concrete, steel, and glass sitting quietly on the ground. But the truth? A building is actually a dynamic, active, force-fighting mechanism. It is locked in this never-ending battle with invisible forces, working around the clock to keep us safe, warm, and comfortable.
Okay, let's dive into this. Here's our blueprint for today. First, we'll look at the building as the ultimate environmental filter. Second, fighting the invisible forces. Third, the rules of equilibrium. Fourth, ground reality and foundations. And finally, framing the perfect space.
Section 1. The ultimate environmental filter, defining livability.
Before we even touch on engineering, steel, or concrete, we really need to reframe the fundamental purpose of any structure. As our sources state, buildings are considered as environmental filter number 2, to create controllable comfort inside the building to achieve livability. So a building isn't just a box, it's an active filter. The primary environment is nature. It's wild, unpredictable, and sometimes downright harsh. The building acts as this secondary filter, constantly screening out the extremes of the physical climate, like intense heat, freezing cold, or driving rain, specifically to protect us and create a nice little pocket of controllable comfort. Now, pulling off this livability doesn't just happen by accident, right? It requires specific structural controls built into the very DNA of the design. First off, architects have to deeply study the physical climate, collecting hard data on rainfall, humidity, and minimum temperatures. Second, the orientation of the building is absolutely crucial. For instance, positioning your long walls towards the north and south and your short walls to the east and west can effectively shield living spaces from intense heat. And third, thermal insulation. This is the actual fabric of the building, meaning the specific thickness and material of the walls and roof. All of these elements work together as one giant environmental filter. Moving on to Section 2, fighting the invisible forces, gravity, wind, and dynamic loads.
So now that we have our comfortable, filtered environment, we have to protect it. And to do that, buildings must battle unseen enemies every single day. The drama of these invisible stresses is absolutely fascinating. A structure is under constant assault. You've got standard gravity loads, which includes the sheer self-weight of the building itself, plus the weight of all of us inside it. You've got thermal expansion and contraction, making the concrete and metal literally breathe and move. You've got horizontal forces like brutal winds and unpredictable earthquakes. And then there are dynamic loads. Think about a massive crowd of people jumping on a floor in rhythm, the jerky movement of an overhead crane, or the constant hum of stationary machinery. Engineers literally have to use thick rubber blocks and heavy springs just to absorb these violent vibrations so they don't tear the entire building apart.
To handle all this chaos, a building relies on a highly disciplined path called a load flow pattern. It's the exact journey a heavy load takes as it travels downwards. First, the load hits the floor slab. The slab passes it to the horizontal beams. The beams then channel that weight into the vertical columns. The columns push it down into the column footings, and finally those footings distribute the massive weight safely into the foundation and the earth below.
It's like a giant puzzle where every piece has a job to do. The horizontal slabs up top transfer their weight to the horizontal beams. Those beams then intersect at the thick vertical columns, carrying the weight downwards, step by step, floor by floor, until it reaches those wide footings resting in the excavated pits at ground level. It is a perfect, continuous chain of strength.
Which brings us to Section 3, the rules of equilibrium. F equals 0 and M equals 0. So how do engineers guarantee that this continuous chain won't snap? Well, they use a set of rigid mathematical rules. To ensure the structure survives the forces we just mapped out, it must achieve complete equilibrium. This boils down to two essential conditions. First, F equals 0. This means all the horizontal and vertical forces acting on the building must perfectly cancel each other out, ensuring the structure doesn't physically move or slide. Second, M equals 0. This is all about balancing moments or torsional forces, ensuring the structure doesn't rotate, twist, or tip over. And honestly, this is the exact science behind leaning towers. When unequal forces generate an unbalanced moment, when M doesn't equal 0, the entire structure begins to rotate and tip over. It must be mathematically ascertained that the building as a whole and every single beam and column within it is perfectly balanced. Now, to nail that perfect balance, engineers sometimes use a wonderfully counterintuitive method called plastic design, especially when working with steel structures. Instead of just calculating what a building should comfortably hold, plastic design is based on calculating the exact loading that will cause a complete collapse of the system. They figure out the exact point where the framework becomes an unstable mechanism. By intentionally determining what it takes to push materials beyond their elastic limits into total failure, engineers can accurately map out vast reserves of strength and build in incredibly robust safety factors.
Okay, so we've got the frame sorted, we know the rules, and we've mapped the load flow. But what actually happens when all these massive, invisible forces finally hit the dirt?
Section 4. Ground Reality and Foundations. Ancient wisdom meets modern geology.
We really have to look downwards here, because the earth beneath a building is literally make or break for its survival. Historically, ancient site selection relied heavily on observing nature, studying the growth patterns of trees and animals to guess the suitability of the soil, and avoiding things they called geopathic stress, which were basically believed to be negative geological features underground. Modern methods, however, are highly analytical. We run topsoil and subsurface testing, we calculate the precise bearing capacity of the soil, and we meticulously map out water tables and aquifers to ensure the ground won't shift, sink, or flood. And thanks to those modern tests, we know that foundation designs must adapt perfectly to their specific geology. It is definitely not a one-size-fits-all situation. For example, if you are building on black cotton soil, which is notorious for shrinking and swelling, your building will face severe floor sinkage. To counteract this, engineers have to use deep, under-reamed piles with pile caps. If a foundation doesn't match the geology, say part of it rests on softer soil that yields, you get what's called differential settlement. This is the other half of the science behind leaning towers. Just look at the Leaning Tower of Pisa, where the soft soil literally sank beneath the immense weight. Conversely, if you are building on hard mirum, a tough, non-cohesive soil with a really high bearing capacity, you can safely use much simpler pad footings. The foundation absolutely must match the ground reality.
Finally, Section 5. Framing the perfect space. Geometric versus rigid planning. Let's see how architectural form and load management actually collide when we start drawing up real-world floor plans. Take a highly unique geometric ground plan like a traditional Mondir temple and compare it with a rigid, repetitive commercial grid. The architecture completely dictates the structural planning here. The complex geometry of a custom layout requires incredibly intricate beam spans and some serious structural gymnastics to transfer weight safely. On the flip side, a commercial grid layout allows for a much more straightforward, repetitive load flow pattern designed for standard loads and uniform apartment layouts.
But whether it's a stunning temple or a towering office block, practical structural planning considerations rule the day. Engineers try to avoid large beam spans because the wider the span, the deeper and heavier the beam must be just to control deflection and sagging. They also have to think carefully about orientation, specifically orienting a column's depth perpendicular to its major bending axis. This gives it maximum moment-resisting capacity. And finally, the whole structural frame must be flawlessly coordinated with things like lifts, escalators, and internal services, as these heavy installations drastically affect the overall design.
The ultimate goal of all this intense planning is total harmony. Every rafter, every wall, and every concrete slab has to work in unison. A successful structure smoothly takes all those violent, invisible forces we discussed and guides them gently and safely down through the frame and directly into those sturdy foundations below. As our source texts beautifully summarize, true structural success isn't just about the rigid math of equilibrium or simply fighting off gravity. A truly successful building achieves a character that implies functional design, creating what they call a perfect marriage of the site, buildings, and surroundings. It's an integrated system of services in total harmony with nature. We've covered a ton of ground today, from load flow patterns to equilibrium equations and the real science behind leaning towers. So I'll leave you with this to chew on. Next time you walk into a building, whether it's your house, your office, or a grand temple, look up at the ceiling, look down at the floor, and ask yourself, what invisible forces is this incredible environmental filter fighting off for you right at this very moment? Thank you so much for joining me for this explainer. Keep your curiosity alive, and I will see you next time.